All right, today we are going to pull back the curtain and unlock the secrets hiding in plain sight, right inside your medicine cabinet.
I mean, have you ever really stopped and looked at a tiny little pill and just thought, how? How on earth does this one little thing know exactly where to go and what to do inside this incredibly complex system that is your body? Well, that's exactly what we're going to break down.
The science that answers that question has a pretty fancy name, pharmacodynamics. I know it's a bit of a mouthful, but the idea behind it is actually super simple and really powerful. It's all about what the drug does to the body, not the other way around. It's the drug story.
So, here's our game plan for today. We're going to start with a drug's basic moves, then zoom in on the body's 4 main targets. From there, we'll get into the classic lock and key idea, touch on how scientists explain it all, and then wrap up with why this is so important for all of us.
Okay, first things first, and this is a really key point. Drugs don't invent new things for your body to do. They can't give you a new ability. Nope. All they can do is modify what's already going on. And they do this using 5 fundamental actions. So a drug can stimulate an organ. Think about caffeine making your heart beat a little faster. It can also cause depression, and we're not talking about mood here, but about reducing an activity, like how an antacid lowers the amount of acid in your stomach. Some drugs work through irritation. Some work by replacing a substance your body is missing, like insulin for a person with diabetes. And finally, some are cytotoxic, which is just a targeted way of killing off invaders, like bacteria or rogue cells, like in cancer.
But how do these drugs know where to go to do all this? I mean, it's not like they have a tiny little GPS, right? They don't just wander around hoping for the best. They are designed with incredible precision to hit very specific targets inside our bodies. Let's take a look at what those targets are.
You know, the huge majority of drugs out there are super picky. They're aiming for one of just 4 types of proteins: enzymes, ion channels, transporters, or receptors. You can think of these as the main command and control centers that medicines are designed to interact with.
So let's kick things off with our first target, enzymes. These guys are the real unsung heroes of your body. They're tiny biological workers that are speeding up just about every chemical reaction happening inside you right now. Everything from digesting your lunch to building new cells.
Now, this image here just perfectly illustrates the whole thing. An enzyme is like a miniature factory assembly line. It takes a substance, which we call the substrate, and it converts it into a product. A drug can come in and act as an inhibitor, which basically means it throws a wrench right into the gears. It jams the machinery, and that stops the product from being made.
And get this, there are 2 main ways a drug can jam that machine. With competitive inhibition, the drug looks so much like the natural substrate that it literally competes for the same parking spot on the enzyme. It's a head-to-head race. But with non-competitive inhibition, the drug is a bit sneakier. It doesn't even bother competing for the main spot. It just binds to a different part of the enzyme, and in doing so, it changes the enzyme's whole shape, making that main spot totally useless. Okay, moving right along to our second target, ion channels. These are basically the gatekeepers of your cells. They control the flow of charged particles, and this flow is absolutely crucial. It's what lets your nerves fire signals and your muscles contract.
And this visual gives us a perfect look. Ion channels are essentially little gateways, or pores, sitting in our cell membranes. And drugs can mess with them in a few clever ways. They can be a blocker and just physically plug the hole. They can be an opener, propping the gate wide open. Or they can be a modulator, which means they just kind of tweak how the gate works. It's all about controlling who gets in and who gets out.
Now our third target is transporters, and they act like tiny shuttle buses moving things across cell membranes. They're really important, but we're actually going to zip right past them for now. Why? Because we need to spend our time on the fourth and by far the most common target for drugs today, receptors. And this brings us to the most classic, most famous analogy in all of pharmacology, the lock and key. Honestly, if you understand this one concept, you're well on your way to understanding how most modern medicines do their job. So what in the world is a receptor? Well, it's a specialized protein, usually hanging out on a cell's surface, that acts like a very specific lock. Its only job is to recognize a very specific chemical signal, which is our key, and when that key fits just right, it triggers a response inside the cell. Okay, this is where it gets really clever. Some drugs are designed to be master keys. We call them agonists. They look just like your body's own natural signals. They fit the lock perfectly, and they turn it to create an effect. But then you have the antagonists. These are like a key that breaks off inside the lock. It fits perfectly, so it slides right in, but it can't turn. It just sits there, completely blocking the real natural key from ever getting in to do its job.
But wait, the plot thickens. There are even more types of keys on the keyring. A partial agonist is like a key that fits, but it only turns the lock part way, so you get a weaker response. And then there's the really weird one, the inverse agonist. Imagine a lock that's always just a little bit on all by itself. Well, this strange key fits and then turns the lock in the opposite direction, shutting it down even more tightly than it was at baseline. So that lock and key idea is a fantastic model. It gets us most of the way there. But, scientists being scientists, they've developed even more sophisticated theories over the years to explain exactly what's happening in that tiny moment when a drug meets its receptor. The first big idea was the occupation theory, and it is beautifully straightforward. It basically says the more receptors you occupy or fill up with a drug, the stronger the effect you're going to get. The maximum possible effect happens when all the available receptors are occupied. Simple as that. But then the rate theory came along and offered a totally different angle. It suggested that maybe the effect isn't just about filling up the locks. Maybe it's about how quickly a key can get in, turn, get out, and then let the next one in. It's the rate, the sheer number of interactions per second that generates the powerful response. And a more modern and really cool idea is the induced fit theory. This one says the lock isn't a rigid piece of metal at all. It's flexible. As the drug, our key, gets close, the receptor actually changes its own shape to create that perfect snug fit. Kind of like a hand sliding into a glove. And that very act of changing shape might be what kicks off the biological response. Phew, okay. So we've gone from a tiny pill down to the molecular level with flexible gloves and through a few different scientific theories. But what's the bottom line? Why does understanding any of this actually matter in our real lives? Well, it matters because this molecular knowledge is the absolute bedrock of modern medicine. By understanding if a drug needs to be a key that unlocks or a key that blocks, scientists can design smarter, better medicines with way fewer side effects. This science also helps us understand why some people's locks are just a little different, causing them to react differently to the same medicine. And it helps doctors predict which keys might get jammed if you put them in the same lock at the same time. At the end of the day, it's all about maximizing the good a medicine can do while minimizing the potential for harm. So the next time you reach into that medicine cabinet, just take a second and think about it. You're not just swallowing a pill. You are unleashing a precise and incredibly complex microscopic drama, a whole cascade of keys searching for their specific locks, all in an effort to set one of your body's processes back on the right track.